Hey guys, last time we talked about the discontinuous conduction mode, and we introduced a few things, analyzed the buck converter, blah blah blah, figured some stuff out, but while I did show you the things that you have to do when you're looking at a converter in DCM, honestly it's not that intuitive, like why things should be the way they are, right? So I wanted to take this time to talk about it a bit more in depth, right? So let's just review what we did last time. So, well, one, we looked at the buck. Right? With, in quotes, real switches. Like they're devices, right? They're silicon devices, but it's still like a model, right? It's still a circuit model. It's not, we haven't really made it very complex in terms of the dynamics of the switches, whatever. But nonetheless, we're using real switches which have specific characteristics, and the one we're interested in with DCM is that diodes can only conduct positive current. Right, and we noticed that when we tried to force the diode current to go negative, instead of conducting negative current, it just shuts off. So when they try to conduct negative current, they shut off. Which then results in a third switching state, which is the characteristic of DCM. Right? This extra switching state is really what characterizes DCM as DCM. Not that the inductor current goes to zero, because it doesn't always go to zero. If there are multiple inductors in the system, then the inductor current can actually go to another value, right? It doesn't have to go to zero. It just happens to be flat in that third switching state. So that's really what's going on, just in general, with DCM. We try to make the current go negative through a diode. The diode can't do that. Third state. What we ended up doing was we did two different things, right? On the one side, we looked at the when this happens. And to do that, we looked at IL is less than delta IL. Right? And it turns out that this condition, looking at the inductor current, makes sense when there's one inductor. Maybe really we should be saying when ID of t, the diode current, equals 0. If this happens, then we go into DCM, and generally it happens when the ripple of the inductor current is larger than the average, right? So we came up with some equations using this expression, right? And we defined this new term called K, and K was 2L over RTS. Right? And then we related this, K, let's just use like a question mark or something. We related it with a sign over it, whatever. We related this K to this other value, Kcrit, which is a function of D. And depending on if K was larger or smaller than Kcrit, then we would be in DCM or CCM. And we could also think about Rcrit. So we think about R as a function of Rcrit. So Rcrit, it turns out we define it, and I'll use this symbol, right? We define K to be 2L over RTS, and we define Rcrit kind of how we define Kcrit. It's going to vary. But I think generally we can say that it looks like 2L over TS times 1 over Kcrit. And that's kind of just rearranging this. Like if you just bring Kcrit down, you can solve for Rcrit in terms of Kcrit, right? And this is a function of D. So as a result, this Rcrit is a function of D. We'll get into this deeper, but basically this is how we decide if we're going to go into DCM. We have some parameters and we have something related to D. The other thing we did was we looked at the conversion ratio. And because we have three states, we end up, if we look at VL, like the average of VL, we end up getting something D1 times something, whatever, plus D2, right, the second switching state. So the first switching state, there's something going on there. And the second switching state, there's something going on there. And there's a third switching state. But because the inductor current should be constant, it turns out that the voltage applied to the inductor in this state is 0, right? So we end up getting 2 variables instead of 1, right? Before we had, when we were solving in CCM, we only had 1 variable, D. Here we have 2, which means we need another equation. And the other equation we got was by, for the buck specifically, or maybe more generally, direct energy transfer conductors, or converters, which are converters where an inductor is connected directly to the output. We looked at the average inductor current, and we equated it to the average output current. And this gave us another expression for D1, D2, right? And by combining these, we were able to find the conversion ratio, and it ended up being quadratic in general. So this stuff ended up being quadratic, right? We got a quadratic solution, which is fine. That is generally what's going to happen. However, there are other kinds of converters where inductors aren't connected directly to the output. And really what we should be looking at, instead of just IL, so this is like one option, is looking at IL if it's connected directly to the output. The other option is looking at the average diode current and equating that to I out. And I'll show you exactly what I'm talking about there. And this will give us another expression for D1 and D2. Okay, so just broadly, this is what we did. And I'm going to use another example to discuss what's going on. Cool. So, just to give you guys a feel for a slightly different situation. So example 2. We're going to look at the buck boost. And I know I haven't introduced this before, but it's a common converter. It happens to be inverting. The specific buck boost happens to be inverting. It's the simpler buck boost, you could say, or the one with fewer components. And you can look up like all the pertinent stuff, but really we're going to try to analyze this in DCM in kind of a quick way. So let's just quickly, right? Let's just quickly show you what it looks like. So great. This is the buck boost converter. It's inverting, which means that the output voltage is negative. Or really, it's inverted from the input. But in this one specifically, it's negative because I've shown that the input is positive, right? Which means if it flips, then the output should be negative. So let's just label some stuff, right? So we have L, we have C, we have Q1, I'll just call it Q, and we have D. And we have R load and V out. Cool. So, to analyze this in DCM, we have to do 2 things, right? Well, we have to figure out when we're in DCM, and we have to figure out what the conversion ratio is. Those are basically our goals. So, let's find out when we're in DCM. So, in this case, we have 1 inductor, so broadly, we can say that we'll be in DCM when IL is less than delta IL. Right? And that's because if the ripple is larger than the average, then at some point in the switching cycle, the current will try to go negative. In this case, it'll go against the direction of the diode, which will reverse bias it. And I'm going to explicitly draw the direction of the current, right? So the current is flowing in this way, right? And you can kind of see why this would invert the output, right? So if we're charging up the inductor this way, when we turn off the MOSFET, we're going to draw current out of this cap, which means that we're going to get plus minus in this direction. Again, I can write plus minus V out here, and it just means that the answer for the conversion ratio is going to be negative in the end. So this is what we need to find. So we have to find two things. We have to find delta IL and IL, the average of the inductor current, right? So really, first, we analyze at the boundary, right? So really, it's like we're thinking about it when IL is equal to delta IL, and this means that CCM equations hold. And that's super important because basically we're going into a realm, the DCM realm, when we don't know what's going on, but we do know what's going on in the CCM realm. So if we use the CCM equations to find out when we go into DCM, then we can bring that back around to figure out what the DCM equation should be. Cool. So we're at the boundary. Let's find the average IL in CCM and the delta IL in CCM, basically. So first, let's use delta IL. So how do we find this? Well, normally we'd have to draw out the waveforms and stuff, and I totally invite you guys to do that. But I'm just going to quickly analyze what's going on, right? So in the first switching interval, we're going to turn on this MOSFET, and we're going to apply VG to the inductor, right? So, and that's going to occur for D, right? The duty ratio, D times TS. That's how long we're going to charge up this inductor. So very quickly, I can say 2 times delta IL, then twice the inductor current ripple, is going to be VG times DTS over L, right? Which means that delta IL is equal to VG DTS for 2L. Great. Halfway there, right? This is one piece that we've got. Now let's get the other piece, IL, the average IL. How do we find this? Typically we do CCB. So we look at the capacitor current in 2 switching intervals, in the 2 switching intervals in CCM, and relate that to the load current. So let's just do that. So IC is equal to 0, right? So in the first subinterval in CCM, right, we're still thinking about the CCM equations. The first subinterval, the diode is going to be off, correct? Which means that the inductor, or the capacitor current, is going to be minus V out over R load. And again, this is fine. Even though I know the output voltage is going to be negative, it's totally fine that I've written this way, as long as I'm consistent throughout the whole operation. So this is D times minus V out over R load, and in the second subinterval, D prime, well, this diode is conducting, which means I'm drawing IL out of this capacitor, so minus IL. In this case, we're assuming we're in DCM, so I can talk about the average IL minus V out over R load. And that's equal to 0. So if we continue up here, we can quickly solve this, right? So we have minus V out over R load in the first interval and minus V out over R load in the second interval, which means that D plus D prime is 1. So we're going to have minus D prime IL is equal to V out over R load. Right? And then again, simplifying, we have the average IL is minus V out over D prime R load. Cool. So there's a minus sign in there, right? That's cool. So we kind of have to do one more thing, right? Typically we don't want to include V out in these equations, or V out and VG. We want them to be in terms of one voltage, and because the input voltage is typically constant and the output voltage is a function of D, typically we replace V out with, basically the conversion ratio M of D times VG. That's what we want to do. So we have to find M of D. So now, some scratch work. Basically we do IVSB. Again, this is equal to 0. And I'll just solve this quickly. So D times VG plus D prime times minus V out is equal to 0, which means V out over VG is equal to minus D over D prime. Sorry, this is a plus. Is equal to minus D over D prime, right? So in the first subinterval, this is conducting, which means we apply VG to the inductor. In the second subinterval, the diode we assume is going to conduct, right? Which means we apply V out to the inductor. That's why we have and the first subinterval Vg and the second V out. This is the conversion ratio. This is M of D, which means we can sub it back into here. So we have IL is equal to minus, well, M of D, which is minus D over D prime, Vg over D prime R load. Great, so these minuses cancel, right? You can see the inversion happening in this conversion ratio. Turns out the minuses cancel, and then we get IL is equal to D over D prime squared, Vg over R load. Great, great. So we have the pieces we need, right? To find out when we're going to be in DCM. We have the average inductor current in CCM, and we have the inductor ripple, again, in CCM. Great. So let's combine these two things, or let's compare them, right? So we transition into DCM when IL is less than delta IL. So IL, D over D prime squared, Vg over R load. And that's going to be less than delta IL, Vg, D, Ts, 2L. Vg, D, Ts over 2L. Okay. And what's nice is we can kind of cancel out these VGs, right? So this VG cancels, D cancels. And then we want to use K, right? So K is equal to 2L over RTS. So we want to get this into this form where we have K is less than some function of D. So I'll just rearrange, right? So I bring 2L up here, TS goes here, and then the D prime comes to the other side. So we have K, which is defined as 2L over RTS, is less than D prime squared, right? I just rearranged this equation to get this, and we're calling this thing 2L over RTS is K. So that means that this is our Kcrit as a function of D. So for the buck boost, Kcrit is D prime squared. Okay, so this is kind of 1/2, right? This is the Kcrit way of thinking about it. And we can also rearrange this, right? So we kind of think about Rcrit. So our Kcrit is D prime squared, and we rearrange for Rcrit. We can say the critical resistance, which is a function of D, is equal to, well, just bringing this down here and bringing the R over here, you can see it's 2L over D prime squared TS. So we came up with these like thresholds, you could say, but what does it mean actually? Well, let's plot it out. Let's do some plots. So I'm going to do a plot for Kcrit as a function of D. And we'll use a nice color, right? Sorry. We'll use purple. Great. So over here we have 1. Over here we have 0.5, right? I'm just kind of dividing this up so it's easier to draw. 0.25, 0.75. All right, so Kcrit as a function of D is D prime squared. So when D is 0, D prime is 1. And when D is 1, D prime is 0. And at D equals 1/2, D prime is equal to 1/2, and D prime squared is equal to 1/4. So we have 1/4, 1/2, 3/2. So we have a quarter here. It's quadratic, right? So we expect some quadratic-like function. If I could draw a quadratic function very well, it would line up perfectly. But what I want to highlight is this boundary. So basically this Kcrit as a function of D is a boundary. It's a boundary between CCM and DCM. So again, just to reiterate, when K which is equal to 2L over RTS, our load TS, the load resistance, when it's less than Kcrit, we're in DCM. Right? That's what this whole reasoning kind of came to. When this variable 2L over RTS is less than some critical value, in this case, it's a function of d prime squared, we're in DCM. So that means that when we're below this line, we'll be in DCM. So this is like the DCM world, right? So depending on where D is, you could have different conditions for L, RTS, for L, R, and the switching period, right? So if you're below this value, whatever number it is, you're going to be in DCM. And then alternatively, when you're above this value, in this world, you're in CCM. And then when you're on this boundary, you're in what's known as the boundary, right? The boundary conduction mode, BCM. Some people call it critical conduction mode, but that's confusing with CCM, so I like to call it BCM. And there's a nice BCD kind of thing going on. Cool. So this is really what it's saying. Like, we have this boundary created by Rcrit, and then depending on how we choose our parameters, L, R, and the switching frequency, will either be in DCM or CCM. And this is kind of the way to think about it. Okay, cool. And we can also think about it in terms of this critical resistance. So let's do that. This is D, and we're going to plot Rcrit as a function of D, right? So this 2L over D over TS is like a constant, you could say. So I'm just going to give you the shape. So we have 0.5, 1, 0.75, 0.25. Okay, so when D is 1, D prime is 0, which means this blows up to infinity. So we have an asymptote over here at D equals 1. So the critical resistance is going to tend towards infinity. Right? And then when D is 0, D prime is 1. So somewhere over here, we're going to have 2L over TS, right? And then I'm just going to, kind of connect it. We have an asymptote over here, and at D equals 0, it intersects the line. Okay, so it's going to be something kind of similar to this, right? So when Rcrit, so we can think about this. If our resistance is smaller, it means our current is larger, which means we'll tend not to be in DCM. So when our load resistance, our load, is greater than Rcrit, which is a function of D, that means we have less current. And conversely, if our load is less than Rcrit, which is a function of D, we have more current. So less current is basically more likely to be in DCM. More current is more likely to be in CCM. Sorry. Less current, more likely to be in DCM. More current, CCM. That's kind of, if the load current is higher, then the average inductor current will tend to be further away from the zero axis, right? So when we're above this critical, this line, when we're above this line, we'll be in DCM. This is the DCM world, right? And when we're below this line, we're in the CCM world. So what is this asymptote saying? It's saying that if we have a really large D, then it's really hard to be in DCM, basically, right? Because we're more likely going to be under this curve, right? And then when D is small, we have to make sure that we're above this 2L over TS. And what's interesting is that this actually has units of resistance, right? If we're saying that the critical resistance, it's L over TS, this has units of ohms. Right? So we're kind of comparing our load resistance to this effective resistance of the inductor. right? Something like that, right? If the inductor is really, really big, then the ripple is going to be small and it's going to be hard to go into DCM, right? So you could say that the effective resistance, or the impedance really of the inductor, is larger. So you're kind of comparing the load resistance to like the impedance of the inductor in a sense. That's what's telling you if you're going to be in DCM or CCM. So these are the kind of plots that you'll see in textbooks, for instance, and this is a helpful way of thinking about it. There's some kind of boundary. You can plot that boundary as a function of D, right? And when you're above that boundary for the resistance, you're in DCM, and when you're below that boundary, you're in CCM, right? So if the current is low, you'll be in DCM, and if current is high, you'll be in CCM. Cool. That's kind of like the conceptual idea anyways. It's high relative to this effective resistance 2L over TS. Great. Okay, so the next thing we want to do, right? So we found out when, and now we want to find out what the conversion ratio is. What is the conversion ratio? So again, I'm going to kind of cheat here and go quickly. And just to remind you, I'll draw the converter here again. So, MOSFET, diode, this is the inductor. So again, we'll have three states. One when the MOSFET is on, one when the diode is on, and one where neither are on. So how do we do this? Well, we use IVSB. That's one step. That'll give us one equation. And the first part is kind of the same as CCM, right? So in the first interval, we apply VG. In the second interval, we apply V out. And again, it's positive. This conducts. And in the third interval, again, the diode tries to conduct negative current, but it can't, which means that the inductor current must be 0. And then when you're not applying a voltage, or when the current is 0 and stays 0, then the voltage must be 0. So we could say D3. In the third interval, the voltage across the inductor equals 0 in the third interval. So we have D1 VG plus D2 V out is equal to 0. This is one equation. The other equation, and this is kind of the important equation, and what I wanted to highlight by why I chose this converter is that the inductor is not connected to the output, right? So we kind of have to inspect this thing. So I'll just draw that out. Sorry, not black. Can't use black here. We have a black background. So, all right, so I'm kind of doing the same thing I did previously, but now we have a diode instead of an inductor. And what I want to highlight is that ID is the only, current has to pass through the inductor to go to the load. So the average ID must be equal to the average load current. So this is slightly different from before, right? Before it was the average inductor current. Here it's the average diode current because the diode is the only thing that's conducting to the load. This is the only way for current to get to the load. So we have to inspect the diode current. And I will just quickly draw what the diode current looks like. So this is ID. This is kind of the other thing you have to do, basically. Either you draw out the inductor current or you draw out the diode current. So TS, D1 TS, D1 plus D2 TS. Right, so in the first subinterval, the diode does not conduct. In the third subinterval, the diode also does not conduct. So current is only flowing to the output in the second subinterval. So if we think about what the inductor current is doing, well, here, I'll define. So ID flows this way, right? It flows in line with the inductor current. So in this first subinterval, I'll draw the inductor current. The inductor current rises up because we're applying a positive voltage to it. In the second subinterval, the inductor current drops down because we're applying a negative voltage to it, right? Because V out should be negative. And then a third, it's 0. So the diode is conducting this inductor current during this time. Cool. So what we're saying here is that the area under this curve, you could say the charge of the diode, divided by Ts is equal to the output current. Right? That's what we're saying with this expression. So let's write it out. Right? So this is the second part is the average ID is equal to the average I out. And we can just say this is I out, which is V out over R load. Great. So what is this average? What is this charge? Well, it's half the base times height. So we have some I peak. And we have this period, which is D2 TS. So we have to find I peak. Capital I peak. I peak is equal to VG. So I peak is equal to, well, it's how long, it's the slope of this current times the time, right? So it's VG over L times D1 TS. Right, because in the first subinterval we apply VG. Cool. And then the base is D2 TS. So Q is equal to half the base times the height over L D1 TS over TS. And this is equal to V out over R load. Cool, so if we eliminate one of these TS's and then simplify, what we get is that we have D2, D1, VG, TS over 2L is equal to V out over R load. Great, so now we just have to kind of put equations 1 and 2 together. So let's do it. We have equation 1, D1 VG plus D2 V out is equal to 0. Equation 2, let's just remind ourselves, D2 D1 VG TS over 2L, my 2's and my L's look very similar, is equal to V out over R load. So we'll use this to solve for D2. D2 is equal to minus V out, D2 is equal to minus D1 VG over V out. So let's just sub that in, right? We can just stick this directly in here, right? Let's use a different color. So D2 is minus D1 VG over V out times VG TS for 2L. I'll put R load over here. R load equals V out. Great. And there's a D in here. Right, there's another D. D1. Okay. So actually it looks like I've forgotten a minus sign. And that minus sign is exactly here. Right? And that's only because if I assume this is a positive V out, then I out should flow in this direction. I out flows in that direction, which means that the average ID is equal to minus average I out. So we have a minus sign here, which means we have a minus sign here and here, right? Minus I out, minus. So we have a minus sign, right? And that is important. So this is equal to minus V out over R load. So we have a minus here. Great. And that's good because these minus signs cancel, right? So this cancels with that. And we get a nice positive equation. So simplifying, D1 squared, VG squared. And I'll bring the V out over to the other side. TS, R load, again, this looks normal, right? Is equal to V out squared. And I'll just rearrange this once more. V out over VG, all squared, is equal to D1 squared, R load, TS over 2L. So this thing, that's equal to 1 over K. How interesting, right? How weird is it that we find this thing here? Cool. So this is 1 over k, so I'm just going to replace this thing with 1 over k because it makes the equation look super nice. So we have V out over Vg squared is equal to d1 squared over k. And now, m of d, well in this case it's actually m of d, r load, ts, and l, all these things, right? Maybe you could say m of dk, I'll just write it out explicitly. And then now simplify it like this. It's equal to V over Vg. And what we're going to do is take roots of both sides. And this results in a positive and a negative solution. And we know because this is an inverting buck boost, the output voltage should be negative, so we take the negative solution. So V out over Vg is equal to minus d over root d1, minus d1 over root k. So this is kind of surprising. This is a little bit surprising. We ended up with this linear function now. So what does this look like? Let's just do one final plot. So the conventional conversion ratio, I'm drawing it like this. This is d. This is m of d. Will be in white. And then we'll draw m of dk, which is like the DCM conversion ratio in red. And yeah, let's do it. So over here we have 1. Just to remind you, this is minus d over d prime. The CCM conversion ratio is minus d over d prime, which means at d equals 0, this is 1, 0.5, 0.25, 0.75. At d equals 0, it's 0. At d equals 1, we have an asymptote, which tends towards minus infinity. So just a quick sketch, it looks something like this, right? And this goes towards minus infinity. However, for DCM, it's linear, right? So we had this crazy inverse function thing going on over here. And then when we go into DCM, it becomes linear, right? With some weird slope, right? So let's just give an example. So it's linear, and I don't know where it's going to cross. Again, this is just drawing a picture to give you guys an idea of what's going on. So it's going to end up somewhere. And it can't be in DCM forever, right? Thinking back all the way back here, it can't be in DCM forever. Sorry. It can't be in DCM forever. Eventually, you're going to be forced into CCM, right? Eventually, when D becomes very, very large, you'll be forced into DCM because there's no K, there's no 2L over RTS that will allow you to achieve DCM, basically. So somewhere over here, you'll be forced into CCM. And maybe it hooks up back here. And I should point out that the intersection of DCM and CCM is actually continuous, right? So the conversion ratio will just kind of, when you transition from DCM to CCM, the conversion ratio will pick up where you left off. It won't be smooth, right? There might be a cusp, but it will be continuous. So it's linear, right? And it has slope 1 over root k. And maybe I'll put a minus 1 over root k is the slope. So as L, TS, and R vary, the slope will also vary, right? Varies with k. Cool. So I hope this gave you a bit more insight into what's going on with DCM, and there's way more resources. Check out Fundamentals of Power Electronics to understand more. But yeah, this is really what's going on with DCM, and really this is like the other half of what you need to know, basically, because this was an indirect energy transfer converter. So maybe I'll do a tutorial version of this where we'll just grind through more specifically with a 2-inductor converter, and we'll see that is actually a little bit different, and like the effective the condition between DCM and CCM looks a little bit different, because we're looking at when the inductor current the diode current tries to go negative. Cool. So the next lecture, not the tutorial, we'll be talking about losses. and also how to model losses in power converters. Cool, thanks.